Hello everyone, I'm Wei Dong. I come from Hong Kong University of Science and Technology. Today I'm going to present our Sigmund paper named as R2T, Instance Optimal Truncation for Differentially Private Query Evaluation with Foreign Keys. This work is drawn with Duke University. Nowadays, the SQL queries over private data are very common. For example, the bank stores the customer information in the relation people with attributes ID and location. If we want to count how many customers are located in region 1, we will release this following query. In this example, the query answer is 8. However, the customer information are usually very private, and releasing the query results directly can break the privacy. For example, if the adversary knows all the information except the P1, it can release the counting query mentioned before. If the result is 8, he will know the P1 lives in region 1. And if the result is 7, he will know the P1 lives in other regions. The solution here is we can add some random noise to the query results. Now, the results here are random variables drawn from some distributions. If these two distributions are very similar, then the adversary cannot distinguish them. That means he cannot know whether the query result is 8 or 7. Thus, the information of P1 can be hidden. This technology is called differential privacy. Let's see the formal definition. The database instance is denoted by I, and we say I and I prime are neighbors if they differ by one user's information. Note that each user can have more than one tuple, and we will discuss this later. A mechanism M is epsilon dp if for any neighbors I and I prime and any output subset Y. The probability Mi in Y and the probability Mi prime in Y differ by at most the factor e to the power epsilon. The epsilon is usually a constant from 0.1 to 10. The dp has a good composition property. If each of M1 and M2 preserves epsilon dp, then their composition preserves 2 epsilon dp. The most common dp mechanism is a Laplace mechanism. Here, the global sensitivity GS is a maximal difference of the query results between any neighbors, and we can construct an epsilon dp mechanism by adding the Laplace noise calibrated to GS over epsilon to the query result. The Laplace mechanism is a worst-case optimal and can handle some simple problems well. For example, for the counting query over single relation, the GS equals to 1. However, the global sensitivity considers the worst case and will be very large in more complex cases like some aggregation query. Here, we still have the relation people, but with an actual attribute deposit. And at this time, we want to count the total deposit for the people living in the region 1. In this example, the result is 140,000. But the global sensitivity should be an upper bound of deposit, like 2 to the power 64, and adding such noise will definitely break the utility. Some people may think, the problem of Laplace mechanism is because it considers the worst case. Actually, the problem exists in every instance. That is, for every instance I, we could find a neighbor I prime such as Qi prime equals to Qi plus GS. In the previous example, we can construct the I prime by changing the deposit of P1 from 10,000 to 2 to the power 64. And then the output will also increase largely. By DP definition, we need to ensure these two results are indistinguishable. One trivial idea is to add 2 to the power 64 noise, but that will destroy the utility for instance I. Thus the question here is, can we avoid such noise on I? The solution is called truncation mechanism. Here, given a truncation threshold tau, we delete the users with contribution higher than tau, and the truncated query result is denoted by Qi tau. Let's follow the previous example. Qi tau is like only counting those deposits less than tau. Given tau equals to 30,000 for I, no people will be truncated, but for I prime, the P1 will be truncated. Here, we can see, for Qi tau, each user can contribute at most tau, thus we only need to add the noise proportional to tau. In this example, we only need 30,000 noise on Qi, which is much smaller than GS 2 to the power 64. Then, the left thing is to select a good tau. For single relation, such tau is found by running DP algorithm to find some quantiles of users' contributions. In the previous example, the DP quantile algorithm can find 20,000, which is the second largest user contribution in Qi and the third largest user contribution in Qi prime. With such method, we achieve error big O log GS times DSI. DSI is the maximal user contribution in Qi, and in this example, that is the maximal deposit of I. It can be shown DSI is instance optimal. That's very intuitive. If we want to hide the information for one user, definitely we at least need to mask its contribution. By the way, the factor log GS is due to the rank error of finding the quantile and is optimal in that problem. Now, let's consider a case where there are multiple relations and join operator. Here, besides of relation people, we have another relation withdraw, and we want to count the total of money withdrawn by the people in region 1. In this case, each user can contain more than one tuple, since each people can withdraw money many times. To handle this, we use foreign key constraints to link users and tuples. And we call the relation storing users as a primary private relation. In this case, that is relation people. Now, let's see the challenge brought by the join operator. In fact, subjoin free query will not introduce any challenge since it can be written as a single relation query. In the previous example, we can join the relation people and the relation withdraw and sum the amounts for each user first. Then, the original query can be written as a sum aggregation query over the new relation. However, different from subjoin free query, subjoins will introduce some challenges. The first one is naive truncation will fail. For example, we have a relation people and relation transaction with attributes from, to, and amount, and we want to count the total amount of transactions. It is just like edge counting query in a weighted graph, where the nodes correspond to a people and each edge is one transaction. And instance I is a 1-to-1 bipartite graph with each edge weight equals to 1,000. Now, we construct I prime by adding one node linked to half of nodes, and the new edges have some random weights. Then, we do a truncation with tau equals to 1,000. For I, no node will be truncated. But for I prime, half of nodes will be truncated, and Qi prime tau becomes 0. In this case, Qi tau and Qi prime tau have a large difference. To address this issue, we propose an LP-based method for Qi tau. That LP can be constructed from the 4 join results. This idea has been used for subgraph counting queries, and here we extend that to SGA queries. The design QI tau has three properties. First, its sensitivity is bounded by tau. Besides, QI tau is at most QI and is equal to QI when tau is larger or equal to DSI. The second challenge is we can now use DP quantile to find the truncation threshold. In the previous example, for instance I, all people have 1,000 contributions, but for instance I prime, the people's contributions is a random sequence. Since these two sequences are totally different, we cannot run the DP algorithm anymore. To address this issue, we propose mechanism raised to the top, which is short as R2T. Here, instead of finding a good tau, we estimate QI directly. As mentioned before, given tau, the global sensitivity of QI tau is tau. Here, we try tau equal to 2, 4, 8, 2GS, and for each QI tau, we add the noise proportional to tau to get tilde QI tau. But the problem here is how to use these tilde QI taus to estimate QI. We can imagine this as a running game. Each tau corresponds to one runner, and he starts at QI tau. The QI is the destination. The noise means the runner can randomly run in both directions, and his final position is tilde QI tau. We hope to use their final positions to estimate the destination. However, when tau is small, the runner has less energy and cannot achieve the destination. When tau is large, the runner is too energetic to be far over the destination. The solution here is we decrease the QI tau by some factors to the lower bound of tilde QI tau. Note that these factors only depend on tau instead of I, and we denote that as check QI tau. Then we add the noise to check QI tau to get tilde QI tau. That is like, we move the starting points of the runners a little bit back so that they cannot run over the destination. Finally, we found the top runner and use its position to estimate the destination. That is why we call our algorithm race to the top. As mentioned before, all runners will not over the destination. And we argue that the top one will not be much lower than the destination, since the runner with tau equal to DSI will not be too low. With such design, R2T can solve SGA queries with error DSI times log.gs times log.gs, which matches the state-of-the-art error for self-join-free queries, except the log factor. To complete the story, we also give the extension to SPGA queries. However, it can be shown for SPGA queries, the error depending on DSI is unachievable, and our algorithm achieves tilde ISI. For the time limit, I will not discuss the details here. Furthermore, our algorithm is easy to implement, and we also give a system. The input here is a SQL query, the primary-private relation, and a set of parameters. The system will first run an SGA query over PostgreSQL engine to extract the relationships between for-join results and users. Then, this information will be fed into Cplex LP solver to solve log.gs number of LPs to get the final result. We also implement some experiments. The first part is the subgraph counting queries under NodeDP, and the second part is SGA queries. R2T has much smaller error than all of state-of-the-art algorithms, except the recursive mechanism. However, the recursive mechanism suffers from a very high computational cost and can only be computed within 6 hours in several cases. Meanwhile, R2T can run all experiments in 6 minutes. That's all my presentation today, and thanks for listening.